Now let's dive into how glaciers erode and deposit sediments and how they can kind of carve the environment and just create it like that. Glaciers can be compared to both a bulldozer and a conveyor belt. Bulldozer in the sense that they really erode their bedrock, they erode the sediments and the environment, and conveyor belt because they bring along with them the product of this erosion. In general, the faster a glacier goes and the more it erodes. But erosion rate will also depend on the type of bedrock. Let's imagine that you have two glaciers. One glacier is sitting on some till, some deformable sediment, and the other is sitting on hard bedrock. Then the glacier that is sitting on till will erode much faster than the glacier that's sitting on bedrock. And if you compare two glaciers, one slow and one fast, sitting on the same kind of bedrock, then the glacier that goes fast will erode its environment faster than the glacier that goes slow. So really have that jointed action of eroding, transporting stuff away. And that's kind of what is shown here in this upper picture. Erosion happens really everywhere. And if a glacier doesn't move at all, we will have almost no erosion happening. So there are kind of two different types of landforms, erosional features and depositional features. So erosional features are created from the material that's taken away by the glaciers, and the depositional features are features created by all that material that the glacier brings along and deposits somewhere, puts somewhere. So we're going to first focus on erosional features. The first one, the U-shaped valleys, hanging valleys, fjords, cirques, and striations. Actually, yeah, we're going to first talk a bit about the moraines and how moraines are created. So whenever a glacier is flowing, it's eroding at the bottom of the ice, but also on the sides. So let's take that glacier that's kind of far away in the picture. As you can see, it's surrounded by rocks on its two sides, and whenever it enters, it merges with another glacier. You create that kind of moraine in the middle. That's called a medial moraine. So medial moraine is some band of rocks, of sediments that is surrounded by ice on its sides. And the interesting thing is that medial moraine, if you trace it back at some point, was what we call lateral moraine. And a lateral moraine is the type of sediments that is kind of pushed on the sides as the glacier advances, that is at the interface between the ice and the rock on the side. So very easy to remember that lateral moraine is surrounded by rock on one side and ice on the other side, and the medial moraine is surrounded by ice on its two sides. So what we see in this picture is that lateral moraines can become medial moraines if the glacier that you're considering merges with another glacier. Here now we're going to talk a bit about U-shaped valleys. So we talked about valley glaciers. They are typically carving valleys in a U-shaped way, in the sense that if you go in the mountains, you're most probably going to see two kinds of valleys, V-shaped or U-shaped. A river is going to erode the bed in the shape of a V. I've never seen the Grand Canyon, but I don't know if it's that applicable there. But basically, that drawing here on the left is representing that. And a glacier will kind of always typically erode the valley in the shape of a U, which is pretty neat because if you go in some places in Alaska where there are no more glaciers, you can determine if a glacier was flowing there before based on the shape of the valley in which you're standing. And you can have another type of feature that is pretty nice, that's called hanging valleys. And that's when you have like a main valley that's probably U-shaped, and you have another valley on the side that it's actually much higher up. We can see that on the drawing here. You have like those two glaciers. You have this big glacier here that's creating U-shaped valley, and you have a small tributary here on the side that is also creating its U-shaped valley. But because this small glacier is not as thick as the other, it's not eroding as far down, and therefore when those two glaciers disappear, you end up with one valley that is higher than the other one. And that's exactly what this picture is showing. And that's what you would expect from Black Rapids Glacier if you were taking all the ice away. So yeah, tributary glaciers can create hanging valleys like that one that intercept the main glaciated region. Fjords are U-shaped valleys that were dug so much that basically the base of the valley is below sea level. So it's just a U-shaped valley filled with some seawater. You have fjords in Kenai Fjords National Park. You have fjords in Greenland, in Norway. They're very impressive features, and they were typically filled with a tidewater glacier specifically at some point. Because when we're talking about a fjord, usually we mean that there's seawater, and then you can sometimes have U-shaped valleys that have a lake at the bottom, but you wouldn't call that a fjord. A fjord is really linked to the water, to the ocean, meaning that at some point there was a tidewater glacier flowing there. In terms of cirques and mountains, so we saw in the first lecture the cirque glaciers that appear whenever there's a kind of a depression in a landscape. Well, those glaciers will also kind of enhance that feature in which they appear. They will carve down that bowl that they were in, and then can also erode mountains almost kind of like a knife. You have a nice example here of the Matterhorn that had glaciers kind of all over that were eroding down the mountain, and that's why you have that's one of the reasons why you can have very, very sharp mountains, like knife edge ridges that are separating different cirque glaciers. So if you look at the Matterhorn, you would have a glacier here, you would have a glacier on the other side, maybe on the other side, I'm not sure. And all those glaciers are eroding the material away. And where those cirques are merging, it's actually pretty sharp. So that's what we call with the knife edge ridge. One of the last erosional features are the striations. They are channels, or like grooves carved in the bedrock, and they are created by the ice that's flowing on them. Actually, not directly the ice. It's not the ice that erodes itself the rock in that case. It's small pebbles or small rocks that are in the ice, imprisoned in the ice, and so they're moving as fast as the glacier, and so you have that rock that's trapped in the ice that's that's eroding or doing some friction here against the bedrock and creating those grooves. And the nice thing with striations is that they are exactly showing us the flow direction of the glacier. So we can do some nice glaciological paleoglaciology, where if you go in a valley and you're not sure about where the glacier was going, in which direction, or how the ice was flowing, you can have this kind of landforms that show you exactly where in the direction in which the ice was moving. So in that case, it was going like maybe from bottom to top of the picture, but it's really obvious in that case. So small quiz prep. What type of glacier carves a fjord? I'll give you a few seconds. And the right answer for that one is answer D, a tidewater glacier. An ice sheet is not going to carve a fjord. Neither is an ice field going to do that. They can, though, flatten entirely mountains. If you go to Norway, mountains are pretty round because most of them were beneath the Fennoscandian ice sheet during the last ice age, and they were eroded away. A cirque glacier is not going to create a fjord. It's not big enough. It's not the right place for that. And a tidewater glacier will create a fjord. Another question: you and your fellow students are mapping geological features in Alaska. You notice striations on the bedrock, and what do they tell you about the valley's geological history? I'll leave you a few seconds. So the answer for that question would be answer B. The valley was eroded by glacial ice flow, because you're in a U-shaped valley probably, and you have striations flowing parallel to the striations. That's what we saw in the previous slide. It wouldn't be perpendicular. That wouldn't make any sense. Really, like think of, I don't know. Just if you take a rock and you you scratched against your, I don't know, your phone or your windshield, you're gonna create a striation that is going in the direction of your movement. So that's exactly the same thing with the ice.